In this video, we're going to look at drawing small molecules. We're going to look at how to take the base geometry and the molecular shape and be able to identify that for any compound we want. So we can know all of these structures. So when we draw a VSEPR structure, there's a couple of key points. If we start with a tetrahedral, we're going to have our central atom, and we have essentially 4 components. This piece here is the wedge. Now your wedge can have the point towards the central atom or away. Both are fine. The dashes, mine are a series of equivalently spaced lines. Yours could be a series that looks like this, or I have also seen them get smaller this way. Mine just tend to be all the same. But the dashes are behind the paper. If you draw the bond as a line, it's considered to be in the plane of the paper. As we draw these, what is not correct is to take your Lewis dot structure, which has 90-degree angles, and to replace them with wedges and dashes. So this would not be a correct structure because we are missing this 109.5-degree angle or its approximation. These are just 90 degrees. So this is not correct where the other one is. There are some videos in other institutions that talk about whether or not we should show lone pairs. In these videos, I will show all lone pairs on both the central atom and the terminal atom. The 3D structure is only required on the central atom, not on a terminal atom. So we are going to look at some small molecules and maybe some medium-sized molecules. So the guidelines. First, draw the Lewis dot structure. To do that, you will determine the valence electrons. Then you will connect. You will create octet on the outer, octet on central. And if it is an octet violator, you will take that into account. Once you have a Lewis dot structure, you will count the number of domains or steric numbers around the central atom. Then you will determine the base geometry or the electron geometry. And then you will use the arrangement of the bonded atoms to determine the molecular geometry or shape. For all of these, you're going to be asked to draw all lone pairs, show the formal charge, and name the base and molecular shapes, or the base geometry and the molecular shape. So for each item, you're going to have 2 structures and 2 names. So let's look at some examples. For XEF2, our valence electrons are 8 plus 2 times 7. So when we put xenon in the center, we're going to put our 2 fluorines out here. When we create octet, we've now used 16 of our 22 electrons. So there are 3 lone pairs left. So based on this, we have a steric number of 5. So we can put our xenon in the center. In this case, I'm actually going to leave it in this arrangement. I'm going to draw our fluorines out here. And we know that the structure looks like this. You can rotate this any way you want in the directions. So we're going to put our 3 lone pairs here. And it asks for you to name the base and the molecular shape. So the base is trigonal bipyramidal, BI. And the MS, or molecular shape, is linear. It also reminds us that we need to think about formal charge. So the formal charge for fluorine is 7 minus half of 2 minus 6, which is 0. The formal charge of xenon is 8 minus half of 4 minus 6, and that's also 0. So there are no formal charges. So we just want to be able to look at these and see how the structure works. So let's look at PCl3. So the valence electrons are 5 plus 3 times 7. So that gives us 26. So we're going to start by connecting our phosphorus to 3 chlorines. We're going to put all of our valence electrons out here. So we've now used 24 of 26. That last pair goes on the center. If we count the number of items around the central atom, then we can then go along and say, okay, there are 4 things connected to phosphorus, which means we're going to start with this geometry. These bonds are all the same, so you can put the lone pair anywhere you like. I'm going to put it at the top. You could have put it on any of the sides. I'm going to go ahead and add back in all of my lone pairs. And so now we have a base tetrahedral and a molecular shape of trigonal pyramidal. And so we also need to confirm that there are no charges on this. Typically, uncharged molecules don't have charges, but sometimes they sneak them in there. So we always want to make sure that we can figure those out. So the formal charge of phosphorus is 5 minus half of 6 minus 2, which is 0. For chlorine, it's 7 minus half of 2 minus 6, also 0. So these two structures here, sorry, that one got a little messy, are your VSEPR structures. And so in order to get this structure, you need to show all of these steps. So let's look at BRF5. So the valence electrons are 7 plus 5 times 7, which is equal to 42. So we have our bromine in the center. We're going to connect immediately our 5 fluorines, and we are going to use valence electrons. So now we have all of these. We are also going to have, so this is 40. We have 2 left, which puts 2 around the central atom, or gives us a steric number of, let's count these up, 1, 2, 3, 4, 5, 6 things, which means we're base octahedral. Put your bromine in the center, connect these 8 things. In a base octahedral, they're all equivalent. So we can put the lone pair anywhere we like. In this case, I'm going to put it on the top, which is different than the base shape we saw, but any molecule can rotate in 3D. So then we're going to add our fluorines. That doesn't look like 2. So we will add in all of our lone pairs. So our base here is octahedral, and our molecular shape is square pyramid. And so you can then determine your formal charges for bromine, which is 7 minus half of 5 minus 2. This would be half of 10, sorry. So that would give you 0. For fluorine, it is 7 minus half of 2 minus 6, also 0. So none of these structures have this. So let's look at 3 more examples. So in this case, we can look at these. So IF2 is actually going to be negative because IF2 non-charged is an odd number of electrons. So we have 7 plus 2 times 7 plus 1 gives us 22. We're going to put our iodine here in the center. We're going to connect our 2 fluorines. We're going to use our lone pairs. So if I've used 16 of 22, and we have this structure, which is a steric number of 5. We'll go ahead and draw this structure. And we're going to put our 2 fluorines here. Go ahead and add all of our lone pairs. So once we see this, we can now say, okay, our base is trigonal bipyramidal. And our molecular shape is linear. So let's look at the formal charges. So in this case, for iodine, it is 7 minus half of 4 minus 6, and that gives you -1. For fluorine, it's 7 minus half of 2 minus 6, and that's 0. So in both structures, you should add a negative charge on the iodine. You should try the ICl4 minus on your own. So let's look at ClNO. So this here is a chlorine. So we have 7 plus 5 plus 6, which gives us 18 valence electrons. So we're going to have a nitrogen connected to an oxygen, connected to a chlorine. I'm going to fill the octet on all of these. So I've used 16, so now we'll add 18. So this structure uses all of our valence electrons, but it doesn't have octet. So we are going to use the oxygen and put them here. Chlorine doesn't make double bonds. So then we have this structure. Or the other alternative would have been this structure. And you should think about the formal charges as to why this top one is the preferred the preferred structure versus the other. So this nitrogen structure has 1, 2, 3 things connected to it. So the nitrogen looks like this. We have a chlorine here. So this one is a little different. So our base is trigonal planar. And our molecular shape is bent. So in this case, we can see that because if you look at just the atoms, it is bent similarly to an AX to E2 structure. So we can see these are formal charges. For chlorine are 7 minus half of 2 minus 6, which is 0. For nitrogen, it is 5 minus half of 6 minus 2, also 0. For oxygen, it is 6 minus half of 4 minus 4, also 0. So this is how you draw a structure. And we're going to work lots of other example problems, or there are worksheets of example problems you can practice on. So these are small molecules, but let's look at something perhaps a little different. So we have a framework for acetic acid, which is CH3COOH. So this tells you the connectivity. It shows you the bonds. So let's take this and go ahead and determine how to draw the structure. But we've got a lot happening and we need to make sure all of the electrons have been accounted for. So it is 4 plus 3 times 1 plus 4 plus 2 times 6 plus 1, and that equals 24 valence electrons. So we've already used 2, 4, 6, 8, 10, 12, 14. So we need to add more around the oxygen. Once we do this, we see that this upper oxygen here has 8, but the carbon it's connected to does not. So I'm going to take away 2 of these and make a double bond. So from this structure, we want to be able to draw a VSEPR structure. So the way we're going to do this is we are going to coordinate off each central atom. So we're going to start by just drawing this structure. Then we're going to draw and add on this part. We will follow by adding this part. In these molecules, you just want to look at one steric center at a time. So for the red carbon, and by that I mean the carbon in the red square, this carbon has a steric number of 4. So we can make a tetrahedral structure. We have a carbon. It looks like this. So now the question becomes, which ones have hydrogens on them and which one is going to be connected to this carbon? Personally, I like to put anything that connects, so this whole row of atoms, in the plane of the board, because it's going to make it easier for them to connect long term. So I'm going to put the carbon here, and we have a hydrogen, hydrogen, hydrogen. So let's look at the carbon in the blue box. This has a steric number of 3. A steric number of 3 has 120-degree bond angles. So they look like this. And it doesn't matter which one is the oxygen, I'm going to put the double bond going down. It doesn't matter which one you choose. So the oxygen in the green box has a steric number of 4. So one of the ones in the plane has already been drawn. So you can, and you just need to draw any of the others. So I'm going to draw one here, and they look like this. The 2 lone pairs and the oxygen can go on any place that you like. I will put the hydrogen here and these 2 oxygens. So we were able to draw this by taking one step at a time. So this is the way that you can do this for any molecule. So we can also do this for one with even a more dynamic framework. So the number of valence electrons is 4 plus 3 times 1 plus 5 plus 2 times 6. So that equals also 24. So now we can connect these together. 1, 2, 3. So that gives us, we've now used 2, 4, 6, 8, 10, 12. Carbon has octet. The oxygens don't. So we're going to add octet to both of these. And this does not work because the nitrogen doesn't. So if you remember back to a previous video, we're going to take one of these sets and give a double bond here. We are going to go ahead and check for formal charges. So carbon is 4 minus half of 8, which is 0. Nitrogen is 5 minus half of 8, which is plus 1. So we have a positive charge here. Oxygen with the star next to it is 6 minus half of 4 minus 4, 0. Oxygen with a square next to it is 6 minus half of 2 minus 6, negative 1. So we do have a negative charge here. This does have a resonance structure. We are only going to draw the VSEPR structure of 1. You would likely be asked to draw both. So I'm going to go ahead and draw my box of atoms that I want to keep in the plane, and I'm going to choose these. They're all connected to my structure. So now I'm just going to differentiate between each steric number. So we have a carbon. I'm going to put it in a green box. We have a nitrogen, and that's going to be in a blue box. So in this case, we only have 2 steric centers. So the carbon has a steric number of 4. We're going to draw that here. I'm going to connect the nitrogen here, put my hydrogens here. From here, this nitrogen has a steric number of 3. So it's going to look like this. They are both oxygens. We can put either one where we'd like. I'm going to put my double bond oxygen here, my other oxygen here. We have a positive charge on the nitrogen, a negative charge on this. Don't forget, this has a resonance structure where the double bond migrates between both oxygens. So we now can skill build all of the different ways that we have looked at different structures, and we can start to see how they come together in 3D.